In our last video, we discussed thermodynamic properties. A thermodynamic property is a characteristic of a system to which we can assign an unambiguous value at any given moment without knowing the history of the system before that moment. The examples of thermodynamic properties include mass, pressure, temperature, volume, density, and many others. All those properties, in fact, all share the same feature. That is, first, we can assign them an unambiguous, that is, unique value at any moment. Right? If you are given an object, obviously you can immediately tell its temperature by using a thermometer. You can measure its mass. You can find its volume. Those values are unique. Anyone with enough knowledge of mathematics and physics and thermodynamics and have enough calculation ability and measurement devices were able to find that unique value, and all those values should agree with each other, right, from different people who do the calculation, who do the measurement. And the second common feature of such properties is that they only depend on the condition of the system at the moment when we do the measurement, right? They have nothing to do with the history before that moment. For example, if you are given an object, obviously you can definitely tell how much mass it has, and it has. You don't need any knowledge of the history of the system before the moment you do the measurement to tell the mass. Out of all these properties, 3 of them are considered as fundamental properties, which are pressure, temperature, and volume. These 3 are regarded as being fundamental simply because they can be directly measured. Pressure. I guess we all know what pressure is, right? For example, here we have some air enclosed in such a piston cylinder. You can see that although the cylinder has weight, but it does not fall. Instead, it is sustained there, stationary. If the reason, of course, is because it is supported by the pressure force of the air enclosed inside the piston cylinder. So if we plot a free body diagram for this piston, we can find that indeed the weight of the piston as well as the pressure force acting upon the top surface of the piston because of the ambient atmospheric pressure are balanced by the pressure force due to the air inside the cylinder. So why do we have such a pressure force? What is the physical reason, physical source of such a pressure? According to physics, we know that air in this piston cylinder, in fact, is made of gigantic number of microscopic particles, okay, atoms or molecules, and those molecules in fact are not stationary. They keep moving around. So when those molecules hit the solid surface, like the bottom surface of this piston, they get reflected back. So such kind of striking and being reflected back of those molecules in fact give rise to the pressure force. Okay, so the situation is pretty much like when you throw a basketball onto a wall. This basketball definitely will strike the wall and gives the wall a certain force, and then it is reflected back, right? Now, if you imagine that you are throwing, billions and trillions and trillions and trillions of such teeny tiny basketballs onto a solid surface, and those basketballs are getting reflected back. If you do this continuously, definitely you will create a force on that wall. And because this gas has so many particles, and those particles keep bombarding the wall, so eventually this gas in fact creates a very uniform force over all the surfaces, all those solid surfaces around the gas. Okay, so such a force is the pressure force. So based on my description of the physical reason of the pressure force, you probably can understand that this force in fact is proportional to the surface area. Okay, it's proportional to the area of the solid surface bonding the gas. So which means the pressure force in fact is pressure times the area. Okay, so this pressure force in fact is proportional to the area. So pressure in fact is the pressure force per unit surface area. For this reason, you can find that the unit of pressure should be, which is the SI unit is Pascal, and 1 Pascal in fact is the same as 1 Newton per square meter. Okay, so it is the same as the unit of force per unit surface area. Okay, 1 Pascal in fact is a very small unit. What I mean is that 1 Pascal of pressure is a pretty small pressure. So how small it is? If you have a quarter, okay, a quarter coin, or any coin, okay, if you are not living in the United States, most likely in your country you also have coins, right? Those metal coins you use as changes when you buy stuff. If you put such a coin on the top of a table, then the weight of the coin is going to give rise to a pressure on that table. Okay, that pressure is about 20 pascals. So this is how small 1 Pascal is. Okay, so 1 Pascal in fact is a quite small pressure. For this reason, it is a lot of times not convenient to simply use Pascal as the unit of pressure, because usually the pressure values we encounter is much greater than 1 Pascal, right? So a lot of times you will find that using units like kilopascal or megapascal or bar is needed. Okay, you need a unit which is much greater than Pascal. For example, 1 kilopascal is of course 1000 pascals. and 1 bar is 100,000 pascals, that is 10 to the 5th pascals, and 1 megapascal is 1 million pascals, that is 10 to the 6th pascals. Sometimes we also use unit like ATM. 1 ATM, that is 1 atmospheric pressure, is equal to 1.013 times 10 to the 5th pascal. Okay, so this value is basically the averaged atmospheric pressure at the sea level. You can see that this value in fact is equal to 1.013 bars, which is very close to 1 bar. So in this course, I will simply treat 1 ATM and 1 bar exchangeable, okay? And because they really only differ by 1%, okay? Roughly 1% of difference. Okay, let's see one example. Suppose here we have a piston cylinder device and we have some air enclosed in this device, and I know that the ambient atmospheric pressure is 1 bar or 100 kilopascals, and the mass of this piston is 20 kilograms, and its end surface area is 0.2 square meters. So the mass is 20 kilograms. Now the question is, what is the pressure of this contained gas here? Okay, what is the pressure of this gas? Okay, to answer this question, we can first draw a free body diagram for this piston. Okay, this is a piston, suppose. Okay, then obviously it has weight, that is gravity force, right? It also feels a pressure force because of the atmospheric pressure upon its top surface, and this force, because of the atmosphere, is equal to the atmospheric pressure then times its top surface area, which is 0.2 square meters. And at the same time, its lower surface also feels a pressure force which points upward. Okay, here it points upward, and its value is the pressure of the air enclosed in this piston cylinder then times A. So since this piston is stationary, it is at an equilibrium state, so we conclude that the upward force, which is the air pressure times A, should balance those downward forces, which are mg then plus PATM times A. So from this equation, you can find this air pressure, which is mg divided by A, then plus PATM times A divided by A, which is simply PATM. Okay, M is 20 kilograms, G 9.81 meters per second squared, divided by A, which is 0.2 square meters. Here, since I'm only using the so-called standard SI units like kilograms, meter per second squared, meter squared, you may find that this result will automatically have the standard SI unit of pressure, which is Pascal. Okay, then plus the atmospheric pressure, which is 10 to 5 pascals. Okay, this mg over A, the contribution of the weight of the piston, gives us it gives us 981 pascals. So the total pressure, the pressure of the air enclosed in the piston cylinder, in fact, is 100,981 pascals. Okay. Okay. Now let's answer a quick question. Suppose here we have a truck. Okay, I will try to draw a truck. Okay, suppose it's a truck. Okay, this truck is driving at a constant and uniform velocity on a highway. Okay, a very smooth, straight highway without any traffic. Okay, suppose inside this truck is a hydrogen balloon. So here we have this balloon. Okay, tied to the floor of the truck. Of course, it is floating, right? And because the truck is moving with constant speed, so this balloon, in fact, the cord that ties the balloon to the floor is vertical. Okay, it's vertically straight. Now suppose the brake is applied. Okay, so the truck now decelerates. The question is, will this balloon move forward, that is to the right, or backward, that is to the left? Okay, you can pause the video and think about it. Okay, the answer is that it is going to move backward. Okay, it's somehow counterintuitive, right? And according to our intuition and daily experience, we may expect that the balloon to move forward, right? Because everything inside this truck has inertia, so when the brake is applied and suddenly the truck slows down quickly, then everything inside the truck has such a tendency to move forward. However, this is not the case for the balloon. Okay, of course, the balloon also has such a natural tendency to move forward. But if you think about the air particles inside this truck, okay, there's air particles inside the truck. They also have such a tendency, right? So they will move forward and accumulate close to the front part of the truck, which makes the pressure becomes a little higher close to the front of the truck. So in fact, this balloon is going to feel a higher pressure on the front side and a little bit lower pressure on the back side. And because of this pressure difference, the balloon is going to move backward. Okay, so its natural trend or tendency of moving forward, in fact, is overcome by the semi-lateral tendency of moving forward of the air particles. Okay, So the balloon effect is going to move backward. Okay, the second quick question. As you climb a mountain, is the atmosphere pressure measured along your way increasing or decreasing? Okay, you can pause the video and think about it. See, here we have a mountain, right? Okay, this is you. Okay, so you climb the mountain. Now, if you measure the air pressure along your way, do you find that this pressure is increasing or decreasing when you climb up the mountain? Okay, I think most of you know the answer. It should decrease, right? The air pressure at a mountain top, in fact, is quite significantly lower than the pressure at the mountain foot, as long as it's really a mountain, not a very small hill or something like that. The reason is pretty simple. If you consider the atmosphere, in an imaginary column, okay, so here I draw an imaginary column in the atmosphere. So here, suppose is the outer edge of our atmosphere around the Earth. Okay, of course, this is the outer space. At this point, the pressure is roughly 0. Okay, at your head, this is the pressure of atmosphere at the ground level. Okay, the very reason that you have a pretty large, in fact, very large atmospheric pressure at the top of your head at the ground level is simply because if you draw a free body diagram of for the air inside this column, you can find that the situation is pretty much like what we had with the piston in our previous example, right? This air inside this column, experiences a gravity force, that is, it has weight, but because its upper surface does not feel any pressure force, because pressure is 0 at the upper surface, so this weight is solely balanced by the pressure force at its bottom, right? So it's P ATM at the ground level, then times area, this surface area, right? So this balances the whole weight of this whole atmosphere column. When you get to the top of the mountain, this column becomes shorter, right? So for this reason, it has less weight. Okay, so the weight becomes less. So for this reason, the pressure force needed also becomes less. Okay, the pressure force needed to balance the weight of this shorter column is also less. So when you go up, in fact, the atmospheric pressure keeps decreasing.